don't worry, I will not be overworking you with too difficult scientific problems. But this evening, I'd like to present you some of our research in the field of mesoscopic solar cells. So we have developed those solar cells, and they're also known under the name of bulk junction cells, or interpenetrating network junction cells, or injection solar cells. There are various names, but the fact is they are of the mesoscopic dimension. And just to remind you, mesoscopic means the feature size is between 2 and 50 nanometers. And so what we have as a system here is actually a molecular system. So the absorber is not a semiconductor, although I love semiconductors. And sometimes we use quantum dots as light absorbers. I'll show you one example in my lecture. The initial embodiment of our solar cell was a molecular device. And let me remind you that the photosynthesis also uses molecules to generate electric charges from light. And so you don't see those charges coming out of the green leaf. So what happens to the charges is they are converted by redox reactions, chemical redox reactions, to the fuels, which we know that we have oxygen and carbohydrates. So here's the light reaction, a dark reaction. It's like a water splitting reaction. And then the hydrogen is used to reduce CO2. And what you see here, actually, on the right side, is a dye-sensitized solar cell. This tree is made in Japan by a company called Toyota. It's a car company. And they have a big research laboratory. And so they're building this tree, which has the fall colors and the green color. And it's a dye-sensitized solar cell. Now, what does that tree do? Well, if you put the light on, you produce electric current, and the veins, you see here, these veins are used to collect the electric currents. These are our current collectors. And the current here is simply used to make the butterfly wave the. It's not a very ambitious application, but it shows the conversion. So when the light turns on, the butterfly starts flapping the wings. And a lot of people in Japan, they like this kind of gadgets. So it's actually being commercially produced now by Toyota. And so, but it's not the gigawatt power or terawatt power we need. So let me just, in the very beginning of my lecture, make a point about the problems we are facing. And this is a slide that comes from Richard Smalley, who's a Nobel Prize-winning chemist from Rice University. And he is now, unfortunately, passed away. He died of cancer 5 years ago, but I knew him well, and he had this problem that he thought energy was the most important one. And I think he clearly had a vision, and he also thought that nanotechnology could help to solve the energy problem. So that was his mission. And so the problem really is that the energy demand is going up, mainly because the world population is increasing. And even though you in Spain, you might use less energy, it doesn't matter. So the consumption will go up because of the developing countries. I don't think I have to explain that to you. So, and you know also the global warming that comes about from the fossils. And you also know that oil is peaking. And so we cannot use the oil reserves to cover this energy gap. Actually, there will be a gap that will be opening up. I don't want to scare you, but that gap in 2050 is predicted to be as much as today's consumption. Today's consumption is 450 exajoules per year. Or if you translate that, if I say exajoules per year, that's a power. But maybe you're not familiar with the units, so that translates into 15 terawatts. And so 15 terawatts is today's consumption. And we need, in the next 40 years, 15 more. So how do you cover this? It will be 30 will be needed in 2050. So we have pollution problem. The challenge is we all like the idea of using carbon-free sources. We need to do that. And so solar energy is certainly there. I mentioned to you the 14 terawatts. Well, 120,000 terawatts are striking the Earth. So you might argue this takes just a small part of this and that will solve the problem. No, not so easy. Okay, so the cost is an issue, and solar energy radiation comes in very diffusely, and so some people think actually it's such a challenge that you need a miracle to solve the problem, solve the equation. And so, well, what's the solution? Well, this amazing quote from Thomas Edison. I don't know whether everybody knows who Thomas Edison was. He's inventor of the light bulb. Okay, so and I think the telephone also, invented the telephone. So just can read what he mentions solar power. And he hoped we don't have to wait until oil and coal run out before we tackle the problem. Well, we're about to run out of oil and coal, so it's time to wake up. And so in Germany, there's a lot of interest in renewable energy, not only in Germany, but I think Germany has played a very important role in bringing the PV with the feed-in tariffs. And Hermann Scheer was a member of parliament. He pushed this through, and unfortunately just passed away. So this just shows the same scenario. Today we are at 500 exajoules, and it goes up, it doubles. And so how do you cover that? Well, there's not much else. I once heard a nuclear physicist say to me, at the end there will be only the sun left. You might as well take that as the truth. And so we need to increasingly use the renewables. And so this has happened. The P market has been growing. It's subsidized, and there was a snack. There was a snack that happened a couple of years ago with the feed-in tariffs here in Spain. You may remember the government kept it, and there was a lot of companies that speculated to sell silicon cells to Spanish people, and that didn't happen. And so the market took a real beating, and today it's not that the market hasn't grown, it's gone up. Not as much as actually of this, Germany alone has probably a third. And so, and they're expecting more, like 13 gigawatts. It's going up, but this has now become a Chinese market, because the Chinese have taken that opportunity to with the subsidies they get from their government, to take over the silicon business. So it's more than 50%. Today you buy panels, silicon panels, the chances are you buy a Chinese silicon panel. So, and so there has been a fallout, unfortunately. This is a scientific group here, but you know, there are economic realities, and the economic reality is that a lot of companies crumbled in their valuation and share values. I don't want to cite examples, but investors didn't like it. Okay, and so now we have to go back and convince the investors that this is something they can earn money, otherwise they will leave. In the last year, in 2009, there was only $100 million invested in PV by the venture capitals. The year before, 500. So you see the dramatic drop in investment. And so this, we also need an unsubsidized market. It's clear that this field, at the end, you have to be able to provide energy at a competitive cost. You cannot depend on the taxpayer forever. And so it's good to launch it, but the subsidy has to come down. And so we need to get cheaper systems and high efficiency. But these are evident characteristics. But something has to, it's not just economy of scale. You're not going to come down to the level. Today, the price of electricity is still 6 times too high from silicon panels. That's a lower limit. Maybe here in Spain, depends where you have your panels. In Switzerland, it will not be 6, or a little bit more. And so that has to come down. And can you make it with economy of scale? Well, you never know. We shouldn't say, but it's going to be difficult. I was in China in September, and I went to Tianjin for the summer Davos conference. Now we have a winter Davos and a summer Davos. I didn't know that until I was invited to this conference, which is very economically oriented and costs $20,000 to get your admission. And so fortunately, I didn't have to pay that. I couldn't afford it. And so I listened to the folks there, and again, this Chinese PV community, the business people, they said they can come down, but we're thinking about a factor of 2. But that will take 5 to 10 years. So economy of scale is not the only way. You can, of course, it comes down, and you go to higher volumes, and it may come down more. But where are we today? It's very hard to say what the real cost of silicon modules is. And so we need some disruptive technologies. And fortunately, the science is always open. You can come in and you have a new idea, come in and challenge. And that's what we will be talking about today. Okay, that's by way of introduction. And so the cell which we have been developing, it uses then a dye, which is a molecule, or semiconductor quantum dots. You can also use those. And so the dye is absorbing light and generates charges. It does not transport electric charges. It just generates electric charges. Think about it. Any p-n junction device, you have that accumulation of tasks. The semiconductor has to generate charges, but it also has to transport the charges. So there is an issue with the accumulation of tasks by the normal p-n junction. Not only that, you have the minority carriers, and you have minority carrier lifetime issues. That's why a solar-grade silicon is 99.9999, got 6 nines. You need that purity to get your minority carrier lifetime in the microsecond time range, and you have a good chance to capture the minorities before they combine with the majority carriers. But we don't have in this cell any minority carriers. That's very important to know. We generate electrons, we inject those in a mundane oxide. It's a semiconductor, so the conduction band of this oxide is used to transport the electrons away. But we don't make no holes. There are no minorities. TiO2 is an N-type semiconductor. We don't even dope it. Sometimes it comes as N-type because of oxygen vacancy. So it's called N-type, but we don't dope it N. We just use it intrinsic. It's an insulator. And by injecting an electron, you make it conductive. So now you might say, well, how do you do that? You have a space charge problem. Well, not so. I'll tell you later how we solve that. And so then we have to also, we generate positive charges. The dye loses an electron, it turns positive, ejects the positive charge in a whole conductor, p-type semiconductor or electrolyte. There are several choices you have here. So later I will show you an example where we don't need any whole conductor. So use quantum dots and they conduct the whole per se. So now, is that a new idea? No, sensitization goes back to very old times. Here you have Dr. Vogel is credited, or Professor Vogel, with inventing the color photography. And then he found that the photoresponse of silver halides is enhanced when you use a dye on it. Eosine was later by Ida introduced. So a lot of this idea of sensitization comes from the color photography. Okay. And then we have this paper by James Moser that a little bit later. That's a publication. In those days, that one page was a publication. Can you imagine? I mean, one paragraph is just a thank you for the technician. I don't know whether you read German, but this is just acknowledgement. And so it takes away 1/4 of the article. And this is the message. We can sensitize silver halide. So it's very similar to what we just saw. I'd like to mention my mentor, Professor Heinz Gerscher, who was a real father figure to me. And he is the pioneer in photoelectrochemical cell. He wasn't the first to work on it, but he's really established the science of it. And he's just such a nice man and a gentle person. Passed away in 1994. Very, very, very big loss for all of us. So I showed you that already. I'm not sure why. Okay, now let me go back. Having an issue here. So how did this whole thing come about? People always say, well, how did you invent that cell? It wasn't invented from one day to the other, okay? That's for sure. And so initially, we work on TiO2 nanocrystals. Our laboratory was the first to make these nanocrystals. Now, who did discover the quantum size effect? Well, a lot of people think that this is Lou Bruce. Recently, I was on a judge in a very prestigious international prize. And somebody said, but this, don't you agree that Lou Bruce discovered? I said, well, to be honest, I first thought I was it, but it's not true. When you go back to a Nature publication, which we wrote, I set the record straight. I gave credit to the Kodak chemist that saw that when he used smaller silver halide crystals, there was a shift in the light absorption, and he interpreted it correctly as a quantum size effect. So he should be credited. Nobody does. And the funny thing, a lot of people are getting awards and prizes, and that record is when I'm on committees, on prize committees, and I'm getting older, I'm getting more in a position, I will see to it that the truth, people get rewarded that are the inventors. So we played around with this in sensitization. We were the first to make TiO2 nanocrystals, no problem, that's sure. And we put them in solution. We put the dye on, did some laser experiments. We found that we could inject charges. So we use, these days we had only nanosecond time resolution. And so we published a paper and said, well, if we put a dye on this ruthenium complex, we can get a strikingly high efficiency of sensitization. That means we can inject the charge in the semiconductor particles, but injection is much faster than recombination. Charges stay well separated. So we used that to build a photoelectrochemical cell. This looks pitiful compared to see the beaker, you see that sheet, that fractal film of titanium oxide. And we had a counter electrode. This was a photoelectrochemical device, some bromide solution. So it looked very much like a makeshift. And I should mention to you that in 1988, I was called up by Pfister Möbel, which is in Switzerland, a very well-known department store for furniture. And so the manager calls me up and he asked me, Professor, what are you doing in your research that is useful? I said, what do you mean useful? All my research. No, useful for the world, for the people. So I said, well, look, I have something which I think may look interesting. We're still very early stage. And he said, well, are you ready to show it to our clients? I said, sure. So we set this experiment up in a department store in Lausanne. But we measured the voltage on the cell, the photo voltage, just 1 volt. We didn't dare to go to the current regime because we would have had to stir the solution. And the stirring required more power than we made with our light. So it was a tricky day, but things advanced. So a few years later, we published a paper in Nature with these nanocrystalline films. And these are the mesoscopic films still being used today. And you see this slide is actually a slide that comes from our colleague Juan Biscot. Some of you might know him. He's a physicist. And I always forget the university where he is from. It's north of Valencia. Bisquat, Juan Bisquat. So anyway, doesn't matter. I'll find it out. And so he's very famous for impedance spectroscopy. He did a major contribution. He's the master that taught us all how to apply impedance spectroscopy to those cells, and this was a huge help for us. So we all are grateful to Juan for his contribution. So then the scale-up happened to module size, and mass production now going on. I was asked about 10 times to bring those cells so seems to be very important. So here are the cells. It's just cut off the production line. You can have a look at it. And so then building integrated photovoltaics is very important because our cells are the only ones that can make windows, translucent windows, produce electric power. So here is a unique selling proposition. When you make solar cells, a lot of people ask you, well, what's so special about your cell? Well, we can say that we're the only ones that can make transparent windows. And that's for building integrated photovoltaics is very important. And so where are we today? So we have a power conversion efficiency under standard conditions of 12%. So that's not bad. I mean, if you take amorphous or micromorphous, if you take amorphous silicon cell, it will be less. If you take micromorphous, it will be less. If you take a tandem, well, you get a little bit more. But we can make tandems that are 16%. So And so the module efficiency is 10.5. That's very close to this cell efficiency. Some people think that's incredible. You can't get. You must lose more than. Well, no. It's this technology very easily scalable because we print our films by screen printing, and it's forgiving. And the only loss you have really is with the fill factor of the cell, because of if your device size increases, you might get some IR loss. And also, if you use a collector, then you lose your active area, will become smaller. But these are aperture area efficiency, not active area, total area efficiency. And you see the cell is promising. Especially important is the payback time, which is less than 1 year. And the life cycle analysis has been done by the companies that deal with the industrial development. And we have one project from Joule 7. It's called DSC Robust, dye-sensitized cells Robust. And actually somebody from the Complutense, the university, Thomas Torres, is a partner. And yeah, Thomas Torres. Yeah. Torre or Torres? Torres. Yeah. So well, now we could stop here. But now I like to give you the flavor of some of the research we're doing and show you some applications. So it's this is an academic society, and let's go a little bit into some of the research we are doing, but not into great details. So the dye sensitized, you have the dye, you have the nanocrystals, and you need some hole conductor, which very often, for example, in this device, they will use the ionic liquid as a hole transporting medium. So you have the iodide that goes to triiodide. This carries a positive charge. And the ionic liquids are promising because there's no issue about evaporation. They don't. It's a salt. So a salt doesn't evaporate, and so they're very, very stable. You don't see any liquids here. They're on the pore and the mesopores. And so this was our invention, to bring this in, the ionic liquid. We patented it, and it's now being applied. And so now, but there are shortcomings. For example, if you take the iodide, triiodide, you have an issue with some losses in the cells. That's the main. You might ask me, why do you have 12% and not 31, which is the maximum efficiency for single junction cells? So where are the losses? There must be huge losses. Well, yeah, there are, no doubt. So where are these losses? One is, the main loss is really that when you excite the dye, it injects. So that's not a problem. There's not a major loss there. So we're doing well on the initial charge separation. Now, the hole is on the dye, the electron is in the oxide. Charges are separated. Now we need to regenerate the dye, and using that redox system or hole conductor, but we haven't really matched those levels. So the Fermi level of the solution, or the nonce potential, is 600 millivolts away from the nonce potential of this dye. This is drawn to scale for the current cells. Very often we have this picture here. See, here's my scale. It's on the hydrogen scale, but you can plot it against vacuum. 0 against hydrogen is minus 4.5 against vacuum. And so when you illuminate the cell, the electrons will move the Fermi level higher and higher because you're accumulating electrons. And so that sets one reference. That's Fermi level in the TiO2 is one important reference, and the other one is the Fermi level solution, or the nonce potential. So the difference is your voltage, and if you give half of the voltage away, that's not good. Okay. So it's not exactly half, but nowadays we have been able to come up with some solution, very promising. So typically our solar cells have a VOC, or open circuit voltage, of 700 millivolts, or 750. If you're lucky, you get 800. But with this new couple, we get the cobalt couple, we get 920. So I have asked my people to, when they ask me, what do you want for Christmas, Professor? I said, go to 1 volt with a cell voltage. It'll be the biggest Christmas present you could do for me. And you know, people are getting very nervous now. It's very close. I hope they're not going to lose courage before the year is over. And so just to show you that, of course, it's important to have a high current, high voltage, and fill factor. These are the figure of merits for a photovoltaic cell. But you can see the mesostructure, how important that is. If I use a single crystal, sensitize it, then there's very little efficiency. This scale is now the external quantum efficiency, or incident photon to current conversion efficiency. So you measure the monochromatic photon flux that is impinging on the cell, and you compare it to the electric current that is produced in the outside circuit. So these two figures, you divide the electric current by the incident photon monochromatic flux, and that gives you this figure. So, well, if it's 0.1, that means 0.1%. Only 0.1% of the incident light is converted to electric current. That's miserable. This is, you might as well put it in, well, that's academic. This is interesting, but has no practical value. But when we use these nanocrystalline film, you see the dye now gets, you have a 3-dimensional junction. And this is the trick, because when the light comes in, it will hit the first particle. Well, a little bit gets absorbed. It hits the next, and it goes through hundreds of particles. And finally, you get the light captured. And every time the light is absorbed, you generate electrons in these particles. And so at the end, I get over 80% conversion of electrons, of photons to electrons, in the spectral range where we have a good light absorption of the dye. And so once we had this result, we knew that we had something interesting, because that's what you need to be competitive with other semiconductor-based systems. So as I said, we're close to photosynthesis. And in photosynthesis, you also have the stacking principle. How does the plant achieve light absorption? It also uses a molecule. Well, light comes in, you have the chlorophyll in those thylakoid membranes. These are the dark green. And so light comes in, hits the first chlorophyll layer, and a little bit is absorbed, and goes through many, many layers. And that's why the leaf is green. Otherwise, the leaf wouldn't look green if you didn't have that stacking. And so I hope you understand that what I'm doing in this mesocopics, I'm just stacking the nanoparticles, like a plant stacks the thylakoid membranes to get the light absorbed. And now comes the critical question. If I go back, a lot of people said, fine, we believe that. It's no big deal. You get a big surface area, so you capture the light. So, but you will not be able to extract the carriers. Here comes the challenge. Because if I inject an electron here in this particle, how can I collect it? What happened? How can I collect it? There's no electric field that will help you to separate the charges. The reason why there's no electric field is that these particles are surrounded by a high ionic strength, screened. And so the field is screened, and so there is no field that drives the charge separation. It's only done by diffusion. So if you write the continuity equation, you can forget about the migration term. There's hardly any migration involved, just diffusion. And so why can we collect? Well, the fact is, if you take that message home, then I think that's very important. The fact is that electrons and holes are not moving in the same material. Electrons move in the oxide, and the holes move in whatever you use in a porous space. And so, of course, they would love to recombine. They love to recombine, but you can control this. The dye itself is an insulator, and so it sits right at the interface. If the electron wants to go back out, has to cross the dye molecule. Many of you are physicists. You know that for each angstrom tunneling, you have 1 over E down. Okay. So if you tunnel over 10 angstroms, you lose 10, e to the minus 10. So that's the attenuation of the rate of electron transfer through the tunneling layer. E to the minus 10 is 10 to the minus 4. So you get 10,000 times attenuation just by having 1 nanometer of dye sitting at the interface. So that's the trick, to control the interfacial back reaction. And so we used also natural dyes. I skip over this. We were interested to use green dyes from nature, so we can use chlorophyll. We don't get that much of a, because there's no attaching group. You see, it's important to have those anchoring groups, the carboxylates. They bind to the titanium ions on the surface by coordinated binding. And so if you use chlorophyll as a sensitizer, we get 20% on the Q band of incident photon to current. That's 8 or 18. That's not bad, but of course that's not what you need. In the solid band, you get a little bit better. But look at this. If we take our best is these mesoporphyrins, very simple molecules, over 70%. Some in the solid band, over 80% conversion of incident light to current. And there's actually a Japanese scientist who followed that up. It's this old work, but he just wrote a review, and he now is up to 5.4% just with those molecules. The natural molecule is 14 milliamps per square centimeter. So we designed another dye, which was also a chlorophyll related, it's a porphyrin, over 11% power conversion efficiency. With a rationally designed dye, you have a donor function, acceptor function, and a chromophore in the middle. And that was actually the idea of our Taiwanese colleagues, Diao and Yi. But we made the cells that gave 11%. And so, see, now we get very good conversion across the spectrum. And it turns out that the cells you make with this is green. It's green. And you know, for some areas in the world, green is a holy color. And so we got a lot of interest from this part of the world to make glass panels that look green. And we will build, actually, our school is building a conference center, and we were asked by the architects to provide a glass facade, our solar cells. We, that means industrial companies. I'm not going to do it. I'm a professor, do research. But we asked the architects, what's your choice of color? We can use red, green, you name it. If you use a near-infrared dye, you can't even see the dye. It looks like a glass panel. So they immediately said green. You want green. So, so that's a green dye that works well, and that's going to be used. And so we also know that the charge separation is a femtosecond reaction from these femtosecond experiments. So when you eject the electron, the positive dye absorption is there within 1 picosecond. It's a femtosecond scale reaction. And then, of course, the charge separation is very, very long. It's a millisecond. And this curve just shows you the natural lifetime of the dye, which is not very long. It's 50 picoseconds. still, even though the lifetime is only 50 picoseconds, you get close to 100% conversion because the injection is so fast, femtoseconds. So let me draw this lecture to an end. I have too much. Let me show you one more slide with the sensitizer. Recently, there has been a new development in Japan, and a ruthenium dye was developed. It has this orange spectral response curve of the photocurrent, and it looks like silicon. It's amazing. It picks up at 1,000 nanometers and goes up to over 80%, and it stays flat. So you can't do that with a molecule. That's the amazing thing. You need the mesoscopic dimension. So let me finish by talking to you a little bit about applications and so. So we need, in the applications, of course, you have to say what's so special. What would the client need to sell? So Americans say anything you can sell is good. So how can you sell our solar cell? If you can sell it, then it's good. If not, you might say then it's not good. So we have this ease of building integration, transparency of multicolor option, flexibility. Yeah, you can't do that with a single crystal silicon. Not possible. So there are some other technologies that thin film, but I challenge them. Where's the roll-to-roll production that produces devices of this type that are stable? So lightweight, low production cost, all this. And we will now look at some of these. I should mention to you that a lot of the slides I will show you now in this remaining 5 minutes are from the Asian region of the world. And a lot of people ask me, why? Why is it happening in Asia? And I have been thinking about this. I thought there must be a deep reason. And of course, there are good scientists, curious people. But I think deep down, the beauty is a religion in Asia. And they just like the beauty of the color. I'll show you some examples. Of course, there are also some beautiful ladies I will show you, but please keep your eyes on the cells. And so these are beautiful colors, okay? And this is, you can't do that with a normal photovoltaic. So here's the some transparent version. This red color is very popular in China. The Chinese just love red color. I don't know why. No, I think it brings luck. Yes, the Chinese New Year, everything is red. Because the red color brings luck. So we are lucky to have a red cell ready for the folks that want to have a red color. This is a commercial sales of street lamps in Japan. So these street lamps, they consist of a transparent, you see the transparency here, a transparent dye-sensitized cell. Underneath you have a battery somewhere, but you have also a light-emitting diode. And so during the day, this captures the light and then it sends it back through the transparent cell. In the night, the light is sent back. These are some screen-printed cells, which are, again, it's beautiful motifs and structuring. And so this you couldn't do. You couldn't print a silicon cell that looks like that. You have troubles. It would cost you a huge amount of money. I don't know whether it's possible even. So somebody, Professor Ma, I just saw her in what was that in? Yeah, in the United States. And she has made the first Chinese motive, which is a dye-sensitized solar cell written in Chinese. And she had the idea to use a black dye to make this panda bear that would use electric power. You see the thing spinning? I mean, it's just amazing what kind of ideas people have. So she showed me that, and these are now from Sony, some windows. These are also photovoltaic cells. The designer at Sony just used those beautiful structures. And just to mention the visit of the German president in September in our university, I don't know whether you know this. This is Christian Wolff. He's a new German president. And he's a very practically minded person. He was on the board of directors of Volkswagen before. And so he checked everything out carefully. You can see his face. He really focused on things. And this is the Sony lamp. Hana Akari means a flower lamp. So the glass is a photovoltaic cell. It captures light from both sides. It's a bifacial cell. As any of our cells, they're always bifacial. We don't have the issue with angular dependence because we can capture light from all angles. So these lamps capture ambient light during the day. You don't have to put them in the sun. And they charge the battery, and at night you get, with an LED, you get the light back. And I mentioned this person here, that's this Doris Leuthard, our Swiss president. Very fortunate to have such a nice president, and her husband. And this is another president, is our school's president, Patrick Ebischer. So again, you see those lamps and the charging of this Walkman from Sony. Sony is heavily committed in this field. It's, for us, very fortunate that they put all their know-how. And they have the record on the module efficiency of 10.5%. This is ICE confirmed, so it's a validated efficiency. This is a Korean invention from having the sunglasses that produce electric power. Here we see some, in Japan again, some larger modules, and see the stability, the 85-85, that means 85 degrees, 85 humidity percent, and that is done exposed for 1,000 hours to this condition. You see the cell is, what you have to do is with your module, you go through those 3 tests. And after the 3 tests, the cumulated tolerance is 5%. This is tough. And so one sun irradiation, no change. That's not an issue. Our cells are very stable under light. Heat cycle, a little bit down, but all stability tests were passed. And so we have these, I showed you these building integrated cells. Company that is very active is Dysol in Australia. And you see a roof here in Newcastle. A steel roofing market, they have some business with Chorus and some rooftop applications. This is for a very useful building. And I showed you this already. And this is some of the modules. The modules are okay. They deliver 20 volts, 3 amps, no problem. This is the G24 plant. So we have these rucksacks now where these are just put on the back. And the visit, we also gave the presidents these keyboards for computers. They are powered by dye-sensitized solar cells. So you don't need to plug them in an electric plug anymore. you can see the two presidents very happy about this. So we also gave them a rucksack. And, Christian was a little bit skeptical, but his wife is very happy. So, and of course, our president, Switzerland, is very familiar with this. So some electric cars. Today I was discussing with some people from Nissan. I think Spain also developed electric cars. This is the way to go. And Nissan will soon bring out a car that is costs $35,000, is fully electric, has 160 kilometers range, and lithium ion, but they need power, so they want to use everything they can. And if you have your car parked, and I mean, you can put panels everywhere on your car, but if you have those flexible, you can really span your, or put them on your garage, a wide collector field for the time when you park your car. And the calculation is that can make a big contribution to the, I saw that today, I had the Nissan people visiting today at lunch. And so this Japanese group just so very happy, they came in within the first 10, running against gallium arsenide cells. But so there's a lot of interest in these car applications. This is production. At the end, let me just say two more things. One is, what's the cost at the end? So a lot of people say the cost, we quote in US dollar per peak watt. Can I ask you, who's familiar in this audience with the notion of peak watt? Okay. Of course, our colleague is. I don't see many hands up. But if I tell you the price per kilowatt hour, you would be familiar with that, wouldn't you? So I think we've got to tell people the truth. How much does 1 kilowatt hour photovoltaic energy, not peak watt. Peak watt is a power unit. So nobody knows really what. It means that a device that makes 1 watt in full sun costs $1. Yeah, but you know, people, they get confused by that. They confuse energy and power. What they really want is energy. Kilowatt hour is an energy unit. And so what if we compare now this is from Dysol. You take a 7% cell and a vertical, this is vertical. 90 degrees means I have put it up vertically and on a facade. This is the solar farming, okay? And you see in the vertical position, if I use that as a facade, the silicon price is higher. It's in US cents per kilowatt hour. So the green bars are for the Dyson size. And that's using 7% module efficiency. So we had a big conference in Colorado. I've been traveling like crazy in the last couple of months. That was one of the stops on my trip. So 200 attendants, a lot of companies interested now in commercial. So let me finish by saying the most important message I want to convey to you is that we have to motivate the young people. And I think there's a big chance here. In Spain, you have a lot of gifted young people. And you have to motivate them to get engaged into this challenge, which is the terawatt challenge I mentioned to you in beginning to meet that challenge. And this is here in China. I was there in this August. I was amazed. There was this student, she had made a panel like this. How did you do that? If somebody asked me to make that panel, I would have a problem doing it myself. And we also have the training these students, high school students, using dyes from natural sources. And they make their own cells. They can afterwards power a radio with it. And the best will get a prize. And we even do this for younger students. So I think what we need to do, we have to get the young people infatuated, passionate about this research. Not only passionate about banks. In Switzerland, a lot of people, it doesn't happen, now there has been, of course, some kind of a dissolution with the banks. But in the early days, you would have trained physicists, they would go to a bank and make a lot of money just for the informatics. So this is very important to educate the youth. And with that, I think I should stop, and thank you for your attention.